Good morning, everybody. We are starting today's lectures with the second lecture of the crash course given by Trujillo, Introduction to KM Theory.
Thank you. Okay, so morning, everyone. So today we're going to work only on circle maps. So this will be our starting point, and I want to consider. So I want to take some irrational number. I want to consider perturbations of the irrational rotation. So taking this like this, and just notation for me always t is equal to r mod 0. Okay, so I want to consider analytic perturbations of this. So one way to see these analytic perturbations, where I could see them as this, right, like this, one, where this will be my perturbation, and I can take this function as analytic function here. So analytic, which is periodic, so I can actually see it as a function in the torus. And since I want this to be a diffeomorphism, the only restriction I have to put is that its derivative is bigger than -1. Okay, this will be analytic perturbation. So how do you see that this actually is a diffeomorphism? Okay, so this condition tells you that phi prime is always increasing. So phi prime of x is equal to derivative of this will be 1, so 1 plus this should be bigger than 0. And if you fix 2 points here and you assume that they have the same image, well, this will translate into x plus alpha plus gamma of x being equal to y plus alpha plus gamma of y, which you can write as x minus y equal to gamma of y minus x, and this you can see as gamma prime of some point I minus x, which will mean that either these are equal or this has to be -1, but I'm assuming that this cannot happen, so this shows that this is injective, this is increasing. I obtain one periodic function, let's say on R, and this will define a diffeomorphism, okay? So this, like this, I could treat my analytic perturbations, yes?
I cannot relate. What is the condition about the derivative of eta?
Sorry, here is eta prime of x bigger than -1. Okay. But as before, I will work with analytic functions. I would like them to be in an analytic domain. So I will need to define, so just recall you what I did last time. So I fix some S0 and I want to define analytic domain of the terms. So how do we do this? Let me introduce something like this. I was considering complex numbers, and I take the ones whose imaginary part is smaller than S, and I was considering this analytic neighborhood. So basically I was just quotienting this by Z. So graphically what I'm doing, I'm just considering this will be this strip. This is a complex strip. Here I have I of S minus I of S. And what I'm doing here is just taking the quotient. So I'm really thinking of just considering this region here, where I identify these two sides. Okay. So here, this is not a two-dimensional torus. I'm just taking this identification to see a complex neighborhood of the real torus, let's say. So this is just a small strip around it. So these are the domains that I consider, and I want to consider analytic functions here. So I will denote by C omega of t S the set of real analytic functions. So everything I will do will be with real analytic. If at some point I forgot to say real analytic, it was real analytic. So take here F real analytic. And I can see this. So if you don't like to see it like here, you can see it here, and you can see it just as a function on the complex strip here. But this time I have two properties. So I want this to be real analytic. And since I want it to be something like a restrict here, I just want it to be one periodic. So for any point I pick, I want this to be one periodic. Okay, so today, every time I speak about analytic functions here, you can think of them as something here or just one periodic functions in this complex strip. Okay, sometimes it will be more useful to see it like that. So now, if I consider something of this sort, yes?
When you say real analytic, is when you restrict to the...
Yeah, exactly. I want this part to be sent to the real numbers. Yes.
What about another horizontal line?
No.
No? Okay, only...
Yeah, only this one. So if I consider this, and now I add some function here. I would like to treat this also as a diffeomorphism in some complex neighborhood, so I want to treat this as a diffeomorphism, and we have something very analogous to what we had here. So we'll just write a small lemma. So if I assume that the norm of this one, the derivative of this one, in this complex domain, so actually I didn't define this, so let me just, I will denote this as norm as the supremum of my function over this domain. So this will be TS or CS, whatever you are thinking of. So if I assume that the derivative of this function in this domain is smaller than 1, then I will have the same thing, and I can see this function phi going from here onto its image as an analytic diffeomorphism. Okay, this time from some complex domains to some complex domain. And now I don't know exactly who this is. So since my function is real analytic, for the moment the only thing I know is that this set, this image, contains this torus, the real torus. But then you can say a little bit more. So if I suppose that this is a small perturbation, so if I say that the norm of my function here is smaller than some sigma, so this is smaller than S, then what you know is that this torus is contained here. Okay? So I can see one of these domains, one of these complex strips, in the image of my diffeomorphism. Okay, this will be useful later, but just to make the analogy, I will mostly consider diffeomorphism of this kind. So I want to convince you that everything I will consider as well-defined diffeomorphisms. So the proof of this part, so I will make just a sketch of the proof. So the proof of this, that this is an analytic diffeo, is entirely analogous. I can show that the derivative is always different from 0 and is injective exactly by the same arguments. So I won't do this part. I just wanted to convince you that this is true. That you can imagine that if this is small, then this happens. And this you can see, say, in the picture with the complex strip. So if you take this TS, so this complex strip here, say like this, and you apply your transformation, so you apply Phi equal to R alpha plus eta. Well, R alpha is just adding alpha, so it preserves all the horizontal lines. And this eta moves things by at most sigma. And since this is real analytic, what is happening? Well, the real line has to be sent into the real line. And these lines will move at most sigma below or sigma above. So I will have something. So imagining what can happen, I will have something like this, but I can really put some real complex strip here. And here I have, this point will be I of S minus sigma. Okay? Is this clear for everyone? So, this is just that the statement I'm going to make now is completely clear. So, our objective today is to prove the following. So, we want to show Arnold linearization theorem. So, to show the theorem, let me graph this. Okay, perhaps it's better to recall something. I forgot. So last time I defined what I called of type alpha 2, gamma 2. So just to recall you, a number, an irrational number, I said it was of type gamma 2 if and only if had the following. So for every two numbers I picked, q different from 0. So sorry, it's a little bit small. Q alpha minus p was bigger or equal than this constant over q to the 1 plus 2. Basically, some kind of Diophantine condition. So just to recall it. And now the statement of the theorem. So what I want to show today. Start by fixing some domain of analyticity, some Diophantine constants, and I will pick a irrational number of type gamma 2. Is it okay if I write very in the corner? Is it okay for everyone to read? Okay. So I do this. And then I can say that there exists some epsilon, which depends only on this constants that I fixed, such that if I pick a function here, which certain smallness, so I suppose that the norm of this is smaller than epsilon 0. Then this perturbation is diffeomorphism so I will just assume here that okay, this I could avoid a little bit, but I just want to convince you that this will be a diffeomorphism already, so I just assume that its derivative is smaller than 1. So it's a proper perturbation. Then, let me not say that... sorry?
So, definition of phi. No.
Next.
Yeah, thank you, but I'm going actually to erase this because I will... Now, because of the lemma, this already is a diffeomorphism, so what I want to say is that if diffeomorphism phi equal to R alpha plus eta has rotation number equal to this value, so has rotation number equal to alpha, then my perturbation phi is analytically conjugated to the rotation. So here when I say analytic conjugated, I want to think of this conjugacy only on the torus. It will be defined in some complex strip, but for the moment use only on the torus, so think of it as I can find some transformation psi from the torus to the torus, so an analytic diffeo. Which conjugates maps, so can say I of phi equal to L alpha composed with phi. Okay? So this is what we're going to do today. Yeah.
If you drop the assumption that the rotation number is alpha, it is still true, but you have a conjugacy to another rotation, or?
So if you assume that this other rotation number is of some type, yes, you can conjugate to some other rotation. So the important thing is that what you perturb, you want this rotation number to have this kind of property. Yeah. This will work. Here I'm just doing it for setting like this, but yeah, if you assume that you perturb
Does it matter what is the type of this another rotation?
So, no, of this one, no. Because basically what you will do in that case is try to write it as something like, you know, let's say your alpha prime. Plus, you know, r alpha minus r alpha prime plus your perturbation.
Okay.
Something like this.
I see, I follow.
So, yeah. Any other
It
questions?
should be phi there, not f.
Yes, you are completely right. Thank you. Thank you. Questions, comments? So this is what we're going to do today. So I really, please, if you have some questions with the statement, say it now. Okay, so now I'm going to probably list most of the things. So now I want to really introduce what are the ideas to prove this kind of statement. So how one shows something like this. So I want to define some kind of scheme that will help me solving this. So this is a KM scheme. So sometimes a KM scheme is compared to a Newton method. So a Newton method it's called sometimes Newton method in Banach spaces. So the idea is the following. I know what I want to do. I know what I want to find. So I want to find something like this. I want to find a conjugacy. Sorry, here I wrote it wrong. This was the conjugacy. Thank you. So I might not be able to do this. So in Newton method, what do? You have your difficult problem. You linearize. Then you find a solution for the linearized problem, and you use the solution in your next step. You start with the next solution. You plug it in. You linearize, and you will repeat. So we're going to see this in this kind of scheme that I'm going to try to sketch a little bit. So my starting point will be, I have some map of this form, right? This belongs to some analytic space of functions. So I'm using already some sub-index because I know what's going to happen. I'm going to define a series of sequences. So yes, I'm introducing this is phi I started with, this is the eta I started with. And so my objective is I want to solve, so the first step is try to solve this. So I want to find a conjugacy that makes H composed with phi0 composed with H equal to R alpha plus this composed with H. So my second step is try to solve this, and by doing this I will look for H with a very particular form. So maybe let me add a sub-index by letting H0 equal to the identity plus some function. So why I'm doing this assumption? Because I'm assuming that I'm perturbing by something very small. So if I want to conjugate back, sorry.
Conjugation,
Yeah. Sorry, thank you. I'm trying to conjugate back to this. So I perturbed and I'm trying to conjugate back to this.
But still not compose in the same way.
Because I don't want to get the reduction. Yes, sorry. H0 composed with alpha. Yeah, thank you. H0 composed with R alpha. Thank you. This is what I'm looking for. So I'm trying to conjugate back to the rotation. And I'm perturbing by something that I'm thinking this as being very small. So if I look for a conjugacy that is close to the identity, let's see, at least seems reasonable, so at least we can try. So I will look for something like this, whose norm, let's say, at least is comparable to the one I started with. So you try to solve this, like this. So there's an intermediate step which is failed to do this, because usually you cannot do, let me call this equation star 0. You will not be able to find a solution right away. So what you do after is to linearize this equation and solve it. So what do I mean by this? I look at this equation. So this equation, if I write it, if I spell it out, it will be R alpha plus 0 composed with identity plus H0 has to be equal to what I have on the other side, identity plus H0 composed with R alpha. Okay, and then what I do is to remove the terms of order, let's say this to the square. Okay, H0 and eta 0 have a comparable size. I will remove these terms. I will try to linearize, and it turns out that we are lucky, and then we can solve this equation. So it turns out that, so we'll see this in a second, but this reduces to something of this kind. This reduces to finding some H0 that verifies this kind of equation.
The order is norm squared, or?
Yes, norm squared. So everything that would be like, you know, squaring the norm of these two. So it turns out that it reduces to something like this, that we will see how to solve. And then once I solve this, what I do is to plug back the solution. So this is my scheme for the moment. So now the next step is to use this solution. So and estimate the error term. Estimate the error term. So what I'm going to do now, imagine that I found this H0 that verifies something like this. Then I want to define P1 as being, what would it be? Being H0 composed with -1, composed with phi 0, composed with H0. But I also want to see it as the rotation plus something. Why? Because I want to repeat this process. I started with something that looked like that. I want to be able to say, okay, I want to repeat this process. But then, if I want to win something, so imagine that this was my Newton method. My objective was to remove this term. I started with something. My objective is to, at each step, make it smaller, in the hope that at some point, either it disappeared, or in the limit it disappeared. So I want to write this thing, so I need to estimate this. So I have a particular formula for this one. It will be just the difference between this minus R alpha. And what I hope is that the norm of this is much smaller than the norm of what I started with. And actually, since I know what is going to happen, I know what will work for me, I want to be this smaller or equal than some power of what I started with. This will be enough for what I want to do. Okay? The idea is just try to make this smaller. So these 3 steps, so if you start, okay, I wrote 4 things. If you have all of this, you can see them, all of them as doing 1 step of my process. And then what happens? Well, I have a new start. So now my new start is, I start with P1 equal to R alpha plus eta 1. And I can exactly repeat the same process. I could try to, okay, now try to solve this, linearize, do everything. So why I'm doing this? So what is the hope of all of this? Because if I repeat this process, what I'm doing is I am building I'm building a sequence of phi n plus 1. Let me write this, which I see always as R alpha plus some perturbation. So, and this, when you spell out all of this process, you can see this as I build a lot of conjugacies. I compose with my initial transformation. And my big hope is that, sorry, here is go to the -1. My big hope is that if I consider this, let me call it psi n, I look at this. My big hope is that then when I go to the limit, I can define something of this sort. I will take the limit of these transformations. I hope that this will be well defined, will be some analytic function in some analytic domain. And then when I take this to the limit, since these error terms are decreasing very fast, so actually if I can repeat this process, what I know about these error terms is that this one is smaller or equal than whatever I started with to this. So it's really, really going very, very fast to 0 if this is more than 1. So what I expect to have is that psi infinity minus 1 composed with phi 0 composed with phi infinity is equal to my rotation. And then I will be done. Okay? So this is, let's say, the scheme of what we want to do.
The convergence would be because it will be the small hns as well, which will have the same comparable norm with eta n's or something.
Exactly. So at each step you are building, so at each step what you have is hn is equal to identity to some hn, and yes, the hn has to have comparable to eta n. Okay? So is the idea clear of what one wants to do?
And if the series of norms of small h n is convergent, we can have a hope for convergence of the compositions of big.
Exactly. That's the idea. So the idea is that if the sum of these things is converging, so that's why I want something that decreases very fast. If the sum of this is converging, then you have a hope for the composition to be well defined. Okay, I was hiding something from you because there is another fear that I didn't want to show right away. The point is that here I start with some domain of analyticity, but this domain starts to decrease. Why? Because as I was saying in this lemma, for example, just starting here, I can define a map, and these maps, are defined from TS, but I can guarantee some inverse in some smaller domain, for example, already. So the moment I start to compose with the inverse, I am forced to somehow start to decrease my domain. I start to have some problems. And it turns out that at every step, you will lose some little piece of your domain. So for example, when you're trying to find this one, the norm that you get here will not be in the same S0 you started with. It's S0 minus you pay a price. And at each step, whatever you are doing, if you are defining this and you are trying to bound the inverse, you will pay a price. And the point is that then this conjugacy is everything. So when you start here at your new start, let's say, eta 1 is defined in some analytic domain, T of S1. But this time the S1 was equal to S0 minus some price that I paid. So the price that I pay is usually, I fix something that I'm going to lose. Every time I will need to lose something. And you will lose something like, some constant time. So let me say, okay, 6 times whatever. You will lose a finite number of whatever you fixed. So the thing is that every time you have to pay a price. So this price that you are allowed to pay, you have to choose it properly as well. If you want everything to work out, because I would like to have something that is analytic in some domain. So this S infinity will be of the form whatever I started with minus, I don't know, fx6, the price I will pay. So it will be something like this. So I will need this to be smaller than whatever I started with if I have some hope. If I want to have some hope. And why is important this price that you pay and why this appears? So let me just give you a quick intuition of why this is happening. So this is mostly because I am using analytic functions. So I have functions that are defined here. And inevitably, I will need to estimate the derivative of this. And I will need to estimate as a function of the normal this one. But this is where being analytic is so good, because if you have a control here, using Cauchy formula, you can bound the derivatives. But there is a price to pay. So if you use Cauchy formula, then you can say, for example, that if you make your domain smaller, then the derivative has something like this, if I'm not mistaken. So why is this? Because you can write the derivative as 1 of ti over some, let's say, some small ball of radius sigma around my point, and here I will have eta of z over w. You will have something like this. And square.
You are checking because eta is real analytic, not complex analytic.
Only on the interval. Here I'm picking already something that's defined in the complex line. So what I'm doing,
Okay.
you know, actually just that gives me a reason to make the picture. So the only thing is I have this my point minus is, is.
This is what I missed. So if you go to the strip, then you
exactly. So
complex analyticity. Okay.
exactly. So I take some point that is a little bit far from here. I make a small ball around it, and using Cauchy, I can obtain a bound. So when you do this, you can really make just the calculation, and you obtain smaller or equal than 1 over 2 pi norm of this in your full domain, and here you be divided by sigma squared, and here you have 2 pi eta, and you find exactly what I said. But then this holds for which numbers? For the numbers whose imaginary part is a little bit far from S. So this holds for all the z that belong to this domain. Okay, so every time I do this, I have to pay. But then notice that I want this to be very small, because I want this to add up. But the moment that you have this very small, my bounds on the derivative are exploding. So there is really some game here of how small is this? How can I compensate by dividing by something very small that actually I know already that will be tending to 0. So there is something very, very, subtle here, but that's why we need this kind of property. I really want this to decrease so fastly that I can compensate by even dividing by something very small. Okay.
Would it be a problem if S infinity is equal to 0?
So the point is that if you can put it equal to 0, in general you can put it as something positive. What can happen is that you are decreasing by a fixed amount, and at some point your process just stops because you cannot continue. But usually if you could take it as equal to 0. If you manage to do it, it will work. So is this more or less clear? Yeah. So please, because this is what I want you to take home. I mean, this is the strategy. So if you have, the most important thing for now is to get the idea of what we're trying to do.
Is this the problem of small domain method?
So not yet. Now it's going to appear. So the thing is that I was telling you, okay, you have to linearize, and I didn't mention it more, but I said, okay, this will reduce to this. So in solving this, you will find what you call small denominators. I will say it in a second. And it's here that it's very important that my alpha has some nice properties. If I want to solve this, I will need my alpha to have something like this. And we'll see this in a second. So now what I want to do is, okay, I describe this process, convince you, yeah, probably it works. Maybe. And I had this step. So I want to show you what happens if I try to solve this, what happens when I linearize, and how to solve this equation. Okay, all good? So let me erase this picture. We don't want to erase that. So let me go quickly about this linearization. So a little bit more details on the linearization. So I was telling you, I will try to solve this equation right away. So I want to say, actually, this will be a lot of equations. So let me drop the suffix 0 for a second. Let me just say, you are trying to solve this. You are trying to solve R alpha plus eta composed with identity plus h of some point x equal to identity plus h composed with R alpha of x. Imagine that I want to find some h that verifies this. So I just open this equation because I told you open up this and remove terms of, let's say, quadratic order in these norms. So I open up this and what I find is, so I really have to look because otherwise I will make many mistakes. So R alpha composed with identity plus h x plus, sorry, this is h, looks like eta, plus eta composed with identity plus h of x. This is equal to identity plus h of x plus alpha. So you open up once more and you can write this as x plus h of x plus alpha plus eta of x plus hx equals to x plus alpha plus h of x plus alpha. I'm just doing the calculations. And now you notice that, okay, there are some things I can remove, x plus alpha, and then you find this equation. Eta of x plus h of x equal to h of x plus alpha minus h of x. But then this is the moment that tell you, okay, me, I don't know how to solve this if I have h here. But then I make my approximation, so I can say, okay, I can, if I treat this as just saying, okay, this is eta of x, because here I'm just thinking that this has a small size and this is a perturbation of the same size. If I find this, then this one I'm telling you I will be able to solve. And then, okay, I made a small approximation, and this is where all this mistake will appear, this eta 1, and this is where things will start to not work. Because if I could solve it right away, I am done. In one step, I finished, I conjugated, but I cannot do it. So this is just to justify why this reduces to this. And then we can try to see where these small divisors appear. So how can I solve this kind of equation? So, questions so far? Because unfortunately now I will have to erase my scheme. So, So my objective now is how to solve this. So given a function here, solve this equation hx plus alpha minus h of x equals to eta of x. And since I am in the circle, I have very powerful tools. I can express this in its Fourier coefficients, and I can find an explicit expression for this. So this equation, at least, what should be the solution will be explicit right away. So if I write eta x, it's Fourier expansion. So if I do something like this. So these Fourier coefficients, I hope I don't get the formula wrong. Forget if I have to normalize or not. You can always express your function like this. And then if I want something to be true, so if I write also h as Fourier coefficients, then I can find an expression for this. So h of z plus alpha minus h of z. Its Fourier coefficient will be of the form h k times exponential of 2 pi I, sorry here, k z k alpha minus 1 exponential of 2 pi I k z. And all that I want is to have this one equal to this one. So I have a particular expression to this one. So if I define, so if we define h of k equal to this coefficient divided by this, so exponential of 2 pi I k alpha minus 1 for k different from 0. And let me say that 0 if k equal to 0. So notice that if k is equal to 0, this always vanishes. So whatever I put in the zeroth coefficient will disappear when I do this. It's just the average, and I'm just removing twice the same. So if you set this like this, at least formally, if I define this function like this, so at least formally for the moment, then, so for the moment this is formally, what you know is that h of z plus alpha minus h of z will be equal to my function minus its average. I will not be able to kill the average of this function because this has zero average. But at least formally, this would happen. So I have my solution. But then what is the problem? What we call small divisors are these terms over here. You see here I have 2 pi I k alpha, and I'm letting k wander around. K is an integer. So it may happen that from time to time I'm very close to 1, and this can get to be very big. And for the moment, if you give me just any irrational number, okay, I know that these are not 0, it's irrational, okay, good enough, but I have no control. So the control comes from this kind of condition. The control comes from saying, okay, you are badly approximate to rational numbers, and then you can give me some bound on this. Using this bound, you can show that this series, defined like this, will actually converge, and this will make the linearized step of my CAM scheme work. So So what I want to do now is to say what kind of estimate you can get. So lemma. So if I suppose that alpha is of type gamma tau, again, if you remember the definition is right over there, then what can I say about these terms? Well, then I can say that exponential of 2 pi I k alpha minus 1 is bigger or equal than 4 times this constant over this to the top plus 1. So I get some bound. So this really looks again like this Diophantine conditions are working all the time. This is what you can get. This for any k different from 0, of course. Okay. So the proof of this is quite simple. It's just some quick calculation. So how do we do this? Again, equations, so I don't want to make mistakes. So the only thing that we know is that for any m that I pick, so let me say that I fix my k. For any m that I pick, I know that k of alpha minus m is bigger or equal than gamma over k to the top plus 1. This is just my definition of being of this type. And now I just want to estimate, so I want to know what this is. So I can write this as k alpha minus exponential of 2 pi I k m. So I can choose my m here. I'm just replacing 1 by this because it will be useful for me. Because what I want to do is to somehow take k alpha to something small, something I know. So I can rewrite this as exponential of 2 pi I m norm of exponential of 2 pi I k alpha minus m minus 1. The norm of this is 1, of course. And then I just use the expression for e to the I, so I can say that this is equal to the cosine of 2 pi k alpha minus m minus 1 plus I sine of the same thing. Then the norm of this is bigger or equal than the norm of its imaginary part, so I just take this sine of 2 pi k alpha minus m. And now if I assume that I pick some m for which this is small, so I can say that this is bigger or equal than 4 times k alpha minus m. So here this is because sine of p of x is bigger or equal than 2 times x if x is smaller or equal than 1/2. So again, the only thing, until here m was not fixed, the only thing is I pick it so that this is small. I can always pick it so that this is smaller than 1/2. And basically that's it. Then I just plug what I knew and I find 4 gamma over k of tau plus 1. Okay, just calculation. And then I can just try to show that this series defined like this will converge. So are there questions so far? So now the only thing we're going to show before time ends is that this actually converges and that I can bound this by something reasonable. So let's try to estimate what would be the norm of this function in this domain. So I will really already decrease something. Yep.
The fact that eta is analytic gives you the exponential decay of eta hat k, which you imply that h hat is also analytic. Is that what you use?
So the point is that I will need, so you're telling me this is analytic, so I already know that this decreases somehow. Yes? I will need that, but again, that will not be enough if I don't have some control on this. So exactly that's what I'm going to do. Now I'm going to do exactly that. I will say I already know something about these coefficients, and then I will estimate this. So what do I need to know about these coefficients? So I want to estimate this, and the first observation is, so first observation, since eta belongs to this space, then I can say that this decreases as, so I don't want to get this wrong either, this decreases like this. Is everyone happy with this? I mean, we can show it, but it's like classical fact, so and since I don't have much time, I think I will skip it, but yeah. Just because you're analytic, you know that this decreases exponentially.
An absolute value of k.
Exponential? Thanks. Yeah, so now I have like very good tools. Now I know exactly how to control this. So the rest becomes a bit of a calculation. So if I pick someone here, so let me treat this as a function defined in the strip. So let me say I have someone here. So I will write it as x plus I, y, which x is just real, and y is smaller than s minus sigma. And I will try to estimate what will be the norm of this. Okay. So let's start. So this by definition is just the sum, k different from 0, of these coefficients, exponential 2 pi I k alpha minus 1, exponential of 2 pi I k times my point, so my point is x plus a1. Okay, so I can put the absolute value inside, I can make my calculation, and I will already replace by the things I know. So I will use this, and I will use this. So what do I get? I get this here, 4 over there, sum of k different from 0. Let's do the calculations. Exponential of minus 2 pi ks over k to the top plus 1.
Go on.
Okay. So the k is above. Dividing here. Wow. I should get all of this. And I lose my point, so actually I have not enough space for my point. So exponential of minus 2 pi ky. Okay, I think this is what you get.
Plus. As part
plus
of the new equation of y.
Yeah.
Yes. So it's increasing.
Sorry, no, but I it gives you a minus, so you get minus. Yeah. But I mean, anyway, k can be negative or positive, so it's not increasing or anything. It's just that now I want to control this part with this part.
Yeah, but y could be negative.
Exactly, yes.
And
But
this
then
is the reason why should we write absolute value of y and plus.
okay. Yeah.
Yeah.
But then you see, this is why I assume that the absolute value of y is smaller than s minus sigma, because here I have a minus and here I have an s. So if you don't mind, since I don't have much space, okay, let's write it again. This s over 4 gamma, some k different from 0, of k tau plus 1 exponential of minus 2 pi k of s minus y so I just want to say that if I use this, I can write this like this. S minus sigma. This is the moment I'm afraid of.
No, y, the absolute value of y probably should be less than sigma, not s minus sigma.
So I can write here
Am I right?
sigma.
No.
Yes.
Yeah, here is
No,
sigma.
that's okay. Yeah. No, it's good. Okay, so I have this. So I can estimate the norm, and I have
Absolute value. Yeah. In the exponent.
Yes, it's your
here. Thank you. So now I just need to estimate this sum, and I will have a bound for my norm. So turns out that you can. Maybe I will just erase over there. So notice that this sum a priori depends on this sigma, and I want to make it disappear, so just quickly over here. I want to estimate this. So I just will compare this to 2 times this integral. And I will make explicit the dependence of this value on sigma by doing a change of variables. So if I just make here u equal to 2 pi sigma t, then it turns out that you can write this. So we'll not do everything, but once you apply this, you can write this as 1 over 2 pi sigma tau plus 2 integral 0 plus infinity of u tau plus 1 exponential of minus u du, which you can recognize as 2 gamma function tau plus 2 over 2 pi sigma tau plus 2. So with all of this, when you put all of this together, what you find is that your norm in some smaller domain look like some constant over whatever you use to some exponent times the norm of this on this domain. Okay? So this is just to convince you that yes, these kind of hypotheses allow you to overcome the small divisors, allow you to linearize, and you get this kind of behavior. And again, you are dividing by something very small, but the idea is that this kind of term will decrease exponentially fast, and you will be able to pick it nicely, even if you pick a sequence of this. So, are there any questions about this? Okay, so this is basically what I wanted to tell you. Just like this is the important part.
So
Yeah.
the next step, sigma would be chosen how? So because you need to guarantee that sigmas converge.
Exactly. So next time, I will just write like, what I did now is I can give you what we call a CAM step, like one step of my induction. I give you one step and then I say, okay, now I really need to iterate. So I need to pick everything nicely, and I will just show you if you pick everything nicely, with this kind of estimates, things work. So that will be next time. Yep.
May I ask a general question?
Of course.
So here, there are many problems in this scheme, but do you have also like negative result in the sense that, for example, if alpha is not of type, then this does not hold?
So the easiest case is when alpha is like, like rationally dependent. When your torus, the dynamics on your torus is not minimal, but it's like, it decomposes in, let's say, periodic orbits. Your orbit.
No, let's get the irrational assumption, but not their frontal.
So, not that I know of. I mean, not that I know of.
So in finite regularities.
So in finite regularity, then you can do it. I mean, in finite regularity, you can show exactly. Then you can really say that there are no invariant tora. But this is because of the regularity. Now, if you ask me in analytic like this, then I don't know. Like in this analytic setting, I wouldn't know. I know that if I remove the regularity assumption, like if you give me C1, C2, you can do this. You can do. You can destroy this invariant tori of anything, even you can destroy them all. In analytic regularity, yeah, it's not so clear.
Any more questions? So let's thank the speaker. Break.
Next time, will you explain the fact that this is actually going to be smaller at the next step? Okay, well, great.